All right, just in time. All right, I'll move me over here so you see that I'm in class and this is live. Okay, Sir Kicks or Ticks comes from doing an actual coordinate. So again, this is 100% review. Here's X, but rehashing it so that those that are behind on this pick this up. Here's Y, so that's why we call this coordinate trig. The terminal side passes through a particular coordinate in a coordinate plane. That's why we're calling this coordinate trig. And that's where we got the Sir Kicks or Ticks instead of SOHCAHTOA. Okay, I'm in Math 2 honors right now. We're about to open up the world of SOHCAHTOA. We're doing what we're doing today, actually. They're almost the exact same notes between the two classes. You guys, this is review and we got to move on. The other class, we get to, do a little bit more, with this stuff to solidify it. Okay, so but we haven't talked about Sir Kicks or Ticks yet with them. We're just talking about triangles and Pythagorean theorem and all this other stuff, and then special triangles that we're going to talk about with you today. So with all that being said, this is already, you should know this. But again, solidify and move on. So ka toa turns into Sir Kicks or Ticks with a coordinate plane in action. All right, but then we're going to move along from that. We're going to talk about, well, first some basic trig stuff. This is from the Wednesday that we first came back. I don't know what the date was, but we already tested you on this, even though we didn't have questions that were like this easy. If I have triangle here, go ahead and write that down real quick. 7, 24, 25. By the way, that would work. That's one of the triples if you look at your old notes that I had you write down. 3, 4, anyone? 3, 4, anyone? 5, 3 squared plus 4 squared equals 5 squared. This one's easy too. 5, 12, anyone? 13. Okay, 5 squared plus 12 squared. This one's a little harder. 8, 15. Don't say 16. It's 17. 8 squared plus 15 squared equals 17 squared. Then the last one I had you right was 7, 24, 25. Those are the first four Pythagorean triples and the ones that students in the past had memorized and we would make them, but I don't think we do that as much anymore. And then the whole point of this is, yeah, we're going to go around Muhammad. So if I'm going to say the sine of A, this isn't a coordinate plane. This isn't Sir Kicks or Ticks. This is SOHCAHTOA. A is the important angle. What side is 7, Muhammad, compared to A? Is it opposite, adjacent, or hypotenuse? Look at it all the way across from A. So what side is that labeled as? Oh no, and that's the person last hour told me. The hypotenuse is opposite the 90-degree angle. So what's the hypotenuse? 25. So we got to get that first, maybe, before we make that mistake. So what does that make 20 or 7? Sorry. According to angle A. Opposite, because it's all the way across. So maybe get your hypotenuse first before you make that mistake. And then what's the last side called, Muhammad? Jason. And then moving on to Alexander, what's the sine of A with these sides identified now? Hopefully you heard the numbers, 7, 24, 25. Okay, so I'll move in on this. So what's the sine of A? So, huh? Yeah, go ahead. Yeah, I'm waiting. Oh no, sine is so over H. There you go. Now we're going to move on. What's cosine? And I'll shrink this down. Ka. Yeah, it's still you, Alexander. And then what's tangent? So it's O. 7 over 24 is correct. And then I'm going to ask one more student about this. Well, now I got to erase this because the next questions ask about sine of B, cosine and tangent of B. That makes B this angle. So Natalie, what's 24? What side is that going to be called now? So it flips who the opposite and adjacent are depending on the angle you're looking at. What does that make 7 then? And then, of course, the hypotenuse is still the hypotenuse. And then what's sine of B? And notice we're not doing anything about finding angle B. We're just saying what is the sine of angle B, which is that fraction. What's cosine of B? And then finally tangent. And then here's what I want you to know about your reading. Of course, you should know that angle A and angle B are complementary because there's a 90-degree angle, and then these other two angles have 90 degrees left to add up to 90. So they're complements of each other. Notice the sine of A end up equaling the cosine of B. It's because A and B are complements of each other. And that is the rule that you should have read when I told you to read and then do that worksheet. How many people did their worksheet? Okay, that was the rule that you read. And here it is in action. All right. And there's also a relationship between tan and cotan, but I don't have cotan written. I'll wait till the next one to describe that one. And secant and cosecant have that relationship as well. So it should have been in the reading. Now, I made a mistake. Here's what I was talking about with the Math 2 honor students. This is what they just looked at today. The idea of a 30, 60, 90 and a 45, 45, 90. And I hope the dog, you remember this when I go through this. And actually, I love this book because it was the first time I've ever seen a book derive, what we should know about sides in all 30, 60, 90 right triangles. So here's what the book does. They create an equilateral triangle. That's what they start off with, which also is equiangular, 60, 60, 60. And then they drop an altitude. And in an isosceles / equilateral triangle, when you drop an altitude, it actually bisects this opposite side and actually makes two congruent triangles completely. That's a true story, a theorem. So with that being said, if I made all of the sides 2, 2, 2, 2 inches, 2 inches, 2 inches, then this side down here is now 1 inch and 1 inch in these two separate triangles. And then what we're going to do with this is try to find x. What is the length of that altitude that was dropped? Or what's the length of that third side in each of these triangles? Oh, and then one more thing. This 60-degree angle certainly gets bisected as well in an equilateral triangle. So there you go. You got a 30, 60, 90. All right. Love this. This is deriving, which makes you understand where this came from instead of just memorizing. And actually, you should go through the process of writing this, just like I said, I think at the beginning with this class about you activate your brain more when you actually write the notes. And I call on you to make your brain still even more activated. But here we go. 1 squared is 1, 2 squared is 4, subtract, and square roots. Now, I do this with my honors math 2 students as well. Algebraically, x is plus minus square root of 3. But this is a geometry question with a length involved. So we only access the positive. And there you go. That's what you're supposed to know in a 30, 60, 90 right triangle. What we would write and what I wrote with my math 3 people was this. Math 2, I mean. We called the 30-degree side something. Let's just call it A. And that's the letter I gave it. Some teachers use S, some books use S, side. Whatever the variable is, you choose whatever you want. But once I get that one, the 60-degree side will be A, whatever that is, times the square root of 3. True story, 100%. I mean, I could change all of this with different numbers. I could make this like 12, 12, and 12. That would make this 6. All right? Then that would end up making this 6 root 3. And then that would make this, well, that is 12 when I said it was 12. So the last side is 2 times whatever the A value is. How many people remember this? Should be everybody. Hiya! There's a karate chop. Because this is something from Math 2 that was very important. What I usually do is use the 1, 2, and root 3 every time in these special triangles instead of A root 3, and 2A. But definitely true there. All right. And then this was a stumbling factor with my other class, so we'll see how it goes here. So go ahead and real quick draw that again. You want to switch out? Yep, go ahead. Just make sure you drop your calculator on the ground. Redraw this triangle, not with A, but it's the orange. Okay, yep. And write those sides again, but using the 30-degree side as 1. And then the 60-degree side would be 1 root 3. And then the 90-degree side would be 2 times 1. And this is true for all 30, 60, 90s, this relationship. And there is no I don't get it on this. There is memorization. You memorize this relationship, that thing with the A root 3, 2A. The quicker you do that, the better your year is going to be because, man, you're going to get sick of these angle measures. You're going to be dealing with them all the way through May. Special right triangles, 30, 60, 90, and then the next one, 45, 45, 90. Okay, so where are we at here? I think we're at Sarah, possibly. Okay, your first question is this. Just like the beginning thing, we have to do this in terms of 30 first. So that angle measure, what side is this called? There we go. This is a SOHCAHTOA because I don't have a coordinate plane, so I got to call that opposite. What side is this always, no matter what? And then what's the third side? What sine of 30 degrees using these sides now? You are correct. Let's move on. What's cosine? All right. And then what's tangent? Now, it seemed that last hour had a bit of a problem with this. I hope eventually you get to this. What is 1 over root 3 rationalized? See if you can do that quick. I hope when you think or see that it's 1 over root 3, you can go to this right away. I hope we can. And I don't know where we're at with our rationalizing. Just have to multiply both top and bottom by root 3. Some will be able to go right to that without having to write that first part. I really hope so. Aiden, what's cosecant of 30 degrees now? You are correct. It's 2. It's the flip of sine. Knowing these relationships, too, takes months for some students to get that sine and cosecant are flips. And then the longer it takes, the longer you're going to get questions wrong. There's nothing I can really do. What's the secant of 30? And I hope you are there. He just told me 2 root 3 over 3. I hope you were able to see 2 over root 3, and then that becomes 2 root 3 over 3. What's the last one? And here, I'll tell you this before you do it. Don't flip this. Flip this. Flip the 1 over root 3. What's cotangent? Root 3 over 1. You flip this, then you get in a rationalization problem. Just kind of extra work that's not needed. And then moving along, Robert, we're going to change stuff here. Well, now the angle that is dictating the SOHCAHTOA is 60. So what does that make root 3? Oh, no. Okay, and if we don't get that right, we got a problem. So what does that make 2? Okay, so what's sorry, now we got our mixed signals. Tell me which is who? There we go. There you go. And then what does that make the last side? This is what good old Danny Samuelis in high school did. Found the adjacent side last because that one made the least sense English-wise. Opposite makes sense. Hypotenuse, I already know. All right, and then what's the sign of 60 now that you have this written out? So then you see these relationships switch here comparative to the 30 degree. Go ahead. Keep going. It's cosine of 60. Ka. Good. And then tangent of 60. It is root 3 over 1. Then when you flip these, we got the same deal going on, I guess is the best way you could say this. And then here we go back to that reading, which I will do at the end of the notes, talk about that co-function, the complement scenario. Notice the sine of 630, is equal to the cosine of 60. It's because they're complements. And that is the thing that you were supposed to read about. But now we can look at some other ones, like the cosecant of 30 equals the secant of 60 because they're complements. And then one last one, green, cotangent of 30 equals the tangent of 60 because they're complements. That was the rule that you read about, and then did some other weird math with it. Okay, and then this one's real easy to derive, and I did derive that with my IM tours. I'll probably make. I told them I was making a video. I'm going to go to the 30, 60, 90 proof as well. And look at that. We can make this anything, but I decided to make a 45, 45, 90 with length 1 inch. Let's just say inch, because that means there's, some real measure there, real world measure that you can understand. All right. And do you know that a 45, 45, 90 has to be isosceles? All right. If the angles are equal, the side opposite are equal. That's a theorem. We don't go too heavy in theorems anymore here at Lockport and proving, but whatever. And to find out what x is, this is simply all I would have to do. Pythagorean theorem. It's a very easy proof of this. 1 squared is 1. 1 plus 1 is 2. Same thing, algebra. I get plus minus root 2 when I solve. But really, in geometry, we can only have positive measures. Now I'm going to do something funky. I could have made this triangle 7 inches long on each side, and I'm just randomly picking that number. Watch what happens. Well, that has to be 7. 7 squared plus 7 squared is not 2. It's 49 plus 49, which is 98. And then I'm going to do this real fast. 98 is 2 times 49. Everybody, what's the square root of 49? 7. So you end up with 7 root 2 when I simply change the sides from 1 to 7. So it proves the point that no matter what I make the legs, A, 45, 45, 90, this side must be whatever A is times the square root of 2. Has to be. All right. And I can play with this all day long with those side measures, make them anything I want. If I made this 12 and 12, that would end up being 12 root 2 through solving. All right. And using the Pythagorean theorem. So this has to be locked in. Now, with that being the case, let's look at our trig. And who are we at here? Abigail? What's the sine of 45 then? You can pick any one of these, pick this one and then, do it. Okay, so sine of 45 would be opposite over hypotenuse. I just need it as a fraction. What would the fraction be? It doesn't matter. Let's use the 7 because it'd be 7 over what? And that's the point. It doesn't matter if it was 1. There's a good question. She asked, what do we want to use? The 1s as the side or the 7? It doesn't matter. The 7s cancel, just like the 1s would kind of cancel. And then what's 1 over root 2 become? And then go ahead and do that simplification for cosine already. What's the final answer for cosine? So you may have used this 45 here opposite over hypotenuse, and then but this is just adjacent over hypotenuse. So what's cosine? It's root 2 over 2. And then what's tangent? Toa. 1. And then when you flip these, don't flip that. Flip the 1 over root 2. Flip the 1 over root 2, and then flipping the 1's easy. And that's the point. You're going to have these. You're going to get sick of these ratios. And I'm really infinitely sad for the students that don't get this memorized. There is no I don't get it. There is memorization of these side measures for the 45, 45, 90, not as bad. 30, 60, 90, that's the one that students kind of struggle with where the sides are. I'll also help you on the 30, 60, 90 if you're listening. Notice the square root of 3 is smaller than 2. So here's another relationship here that you should, because students put these in the wrong spot. The 30-degree side, that is the smallest. The smallest side is always opposite the smallest angle in a triangle. Root 3 is smaller than root 4. The hypotenuse should be the biggest. 2 times a is bigger than root 3 times a. And then this one's in the middle, somewhere in between. So sometimes people put the sides in the wrong spot, and there's you're going against that basic geometry concept, right? So just make sure you're aware of that as well, and then knowing where these or having those memorized, blah blah blah. Now I'm not going to leave this up here. You actually have to do this in your homework, but this chart is actually what we just did. Okay, it's just putting this in a nice chart format. You can open this up later and look at this yourself. I'm not going to do that. So you're ready for the homework. It actually is already kind of done. You just have to redo it, and I'll talk about that after the video. But I am going to talk about what you should have read about. All right, and this is what your reading was about, just to do a couple of these, and then we'll close it off for the day. This is the co-function / complement that you were supposed to read and do that first assignment Thursday or Friday. And really, these say the same thing. Sine of an angle equals cosine of its complement, and vice versa. Secant and cosecant have that relationship as well. Tangent and cotangent. I talked about it throughout all of the notes today. So when they ask a silly little question like this, write each function in terms of its cofunction, they're asking you to do that complement idea. What is true in terms of these complement relationships? Co-function, complement, COCO. So cosine of 52 is equal to sine of, what's the answer, class? Don't say 52. Sine of what? 38. Then you can check this on your calculator if you have your calculator in degrees. If you type the cosine of 52, press enter. Sine of, students actually doing it, nice. Sine of 38, press enter. You'll get the same weird decimal. The decimal is exactly the same though. Now, do you have a calculator for this? You don't have a cotan button on most calculators, so this one you can't test. But cotan of what? Tan is equal to cotan of what? Not 16. It's a teen. 19. And then secant of 24 is equal to CSC of 66. These you can't test because you don't have those buttons. And that's going to be a later video that I'll put on the calendar that Mrs. Gray made about dealing with your calculator. How would you type cosecant of 66 degrees on your calculator? You got to do something funky. You got to use your reciprocal ideas. All right, and then this is the kind of question that you had in your homework. And if you didn't read, then I'm enabling you right now and going through this real quick. Okay, so how could this possibly be equal? Cosine of this equals the sine of that. Well, the only way that could be equal is if these two were complements of each other. So this is why I wrote, or actually Mrs. Westberg wrote this. If sine equals cosine, then these two angles have to be, by default, complementary. And that's the most direct way to solve a question like this. Theta is just a variable. Now, I told you to read. The example showed something different. I think they showed this. They showed cosine of this equals, I'm going to change this to in terms of cosine, but using my identity, it's 90 minus this angle measure, and that must be in parentheses. And then they drop the cosines. Because if cosine of this equals cosine of that, then this has to equal that. I think the second way is much easier. All right. And that's why I don't really want to see you do that. Okay. But, whatever. I told you to read. So if you validly understand that method, it's totally cool. All right. Trying to move this. There we go. For theta, just, think of theta as x. Don't get scared. And I think we end up getting 21. Now, that's what I don't want to put a degree measure on that. It's not until you plug it in that you should name the angles, but 21 plus 4 is 25. 3 times 21 is 63 plus 2 is 65. 25 and 65 are complements, so we're all good. All right, it exercises that idea with that known. Okay, I'll stop sharing. That's pretty much it for the day. I'm going to talk to the class about the completing the worksheet kind of thing.